Let me. Go ahead. I'll find it. What's the question?
Sir.
This one?
Yes, sir.
Mm-hmm.
Seeing that that I1 will pass through the 2 ohm resistor, sir. When analyzing the circuit, sir, to find like the V1 over I1, would it be a case where I should ignore the 2 at the either ends and concentrate on the 4, the 3, and the other 4 ohm resistor, sir?
So, first thing, that word is a very dangerous word in networks. Ignore. Okay. All right? So we can't ignore anything.
Okay, sir.
So the first thing you want to do, as we said, we asked you to use first principles. So if you are using first principles, you're finding admittance. Now, since you're using first principles, how do you define these parameters? It's the first place you need to begin with the definition.
A short circuit, sir.
Sir, include I1, I2, V1, and V2.
No, but I'm saying, what's the definition? What's the definition that your definitions you're going to be looking at? We're talking about Y11. What's Y11?
The short circuit.
The
short circuit impedance.
First, it's Y, so it's what?
Short circuit input impedance.
Oh, no, it's Y.
Oh,
admittance.
So huh?
Admittance.
Admittance, all right? So we know that it is I over V, and it's 1, 1, so it's I1 over V1, yes?
Yes, sir.
And that is true under what condition? What's the condition for this to be true?
V2 equals 0, sir.
So that is true when V2
is short circuited
and V2 is equal to 0. So you're going to start with the definition. Of course, this is I1. That's V1. This is V2. That's I2. So I2 is 0. So what are we doing to port 2?
Short circuit in port 2.
All right. So we are closing that. And if we want a relationship between I1 and V1, what would that look like? What is I1? How is I1 and V1 connected by virtue of the circuit that we have here?
There's a total admittance.
All right, so give me the expression.
So, it would be the inverse of 2 in series with.
No man. Don't give me. Don't work it out for me. Just give me how are these two connected by virtue of the circuit that we have here? Just give me an expression that connects the two. P1 equal RT times I1. But do you agree with that?
Yes, sir.
That's how they're connected. All right? So what you want to find then is RT. Isn't that so?
Yes, sir.
RT would be the total resistance of the circuit. So I1, because you want I1 over V1, then 1 over RT would give you Y11.
Okay, sir.
You see, when I say go back to first principles, that's what you have to do. Go back to first principles. Or use first principles. You do exactly that. you have the definite, with that short circuited, you can find Y21, right? So Y21 would be I2 over V1. The question is, based on where I2 is, how is V1 related to this? Of course, you would have had the resistance equation. So this is in series with everything that is there. So you do voltage divider to find what component of V1 is at this point. You know that that voltage would be the same at that point. So you then do voltage divider again to get the voltage here. Yes? And the voltage here would be the same across that. So in a sense, gentlemen, what you are doing for this question is just a repeated application of Ohm's law. This is networks 1. So you are just using those principles to come back to that. And at the end, because you don't have values for V1, V2, I1, and I2, that is, I suppose, where your challenge really is. But
Yes, sir.
it is important that you appreciate how to use first principle application to do your analysis. And I really need you to complete this problem before we get started tomorrow, because I certainly will not be stopping to go through this type of analysis. All right, we have to step it up now. All right. All right. So,
Sir,
yes.
the first principle, right? Isn't that the one that you apply the I2 equals 0 and you just do the substitution?
Okay.
Sir, for my matrix, I got 50, 16, and 16, 50. All divided by 11.
I don't know what the answers are. But you said something about I2 being equal to 0.
Yes.
But those for the when the currents are 0, you are looking at open circuit parameters, right? So it means that you would be finding the Z parameters.
Yeah. So for the Z11, I did V1 over I1. And with the I2 equals 0, I had the 2 in series with 4, parallel 3 plus 4.
All right, folks. All right, Lamanja, give me the impedance parameters that you calculated.
All right, for Z11, I got 50 over 11.
All right, so you have 50. The other one?
6Z12, I got 16.
Mm-hmm.
For Z21, I got 16. And for Z22, I got 50. And I have an outside the bracket 1 over 11.
I don't know if this is right. If it's right, that's good. What do you need to do? These are the open circuit parameters. All right? What you need to do to determine whether or not you're correct is to then go and find the Y parameters. Yes, whatever these are, whatever they work out to be. So you're going to find the Y parameters, again from first principles. Yes? And once you have that, then Y inverse, whatever this works out to be, must be equal to Z. So that's how you compare. That's how you determine whether or not what you have done is correct. But I want you to, this is the key here. I want you to use first principles. So again, start from the definition, and by virtue of the definition, develop these parameters or determine these parameters. And then at the end, you do the conversion to see whether or not what you have done is correct. All right. Okay. So what we're going to be doing today, we're going to take it a little step further. And what you would have recognized by now, and we introduced it briefly in the last class. We said that the hybrid parameters, you have used them in the H to V model for your transistor. For those who would have done your electronics or looked at electronic circuits already, you would know that as part of an amplifier circuit, you have your transistor, you have things like your Darlington pair and all of that fancy stuff, where you're connecting two transistors together, or you're connecting a set of resistors to a transistor. You may be connecting a power line to another power line. Yes. The bottom line is 2-port networks, you're going to have interconnection. So remember, when we started out, we also gave some examples of 2-port networks where you may do coupling. So you have transformer coupling. So you are coupling 2 stages of your amplifier circuit using transformers. Now, the transformer, as we explained earlier, is a 2-port network. So too the transistor. So where we are going today is just to look at the connection of these 2-port networks. And there are one of 3 potential connections. And what we want to start with is your parallel connection. How do we analyze networks that are connected in parallel? Now, before we even get to how we analyze them, one of the things we want to establish is how do we identify that they are in parallel? And if you go back to what we said in networks 1, 2 elements are considered to be in parallel if the current entering the node connecting them divides. That's how we define parallel connections. You recall? So we're going to look at these 2 networks. Here we have network A, we have network B, and we are saying that they are in parallel. So I'm just going to trace for you why they are in parallel. And of course, again, based on what we had said back in networks 1, or should I say by extension, if the current entering the node divides them, and we also said that the voltages across them would be the same because the potential at either end of the 2 elements would be the same. So the potential difference across them would be the same. Fair enough? So we are going back to those basic definitions in looking at the parallel connection of our network. So here we have networks A and network B. Here I have current I1, and current I1 comes to this node. So here's the node. Yep. And the current then divides. So we have I1A. All right. So we have one current there, and we have another current coming here. So we have our 2 currents. So I1 divides into current 1 and current 2. I1 or current 1 now forms the input current to network A, and so that would be I1A. And current 2 forms the input current to network B, and that is I1B. So obviously we are satisfying that first criterion, which is that the current entering the node, which connects the 2 elements, yes, that current divides. So it divides between network A and network B. Everybody see that? There any questions with that one? Anybody unclear as to what I just outlined?
Yeah,
Okay.
so let's go back over that last one.
All right, so we have I1. It enters our node. All right, so it enters the node. And it divides. All right. So in my diagram, I'm showing one as black and one as red. So network B is the red. It also satisfies the standard that we had established for two-port networks, which is that the current on the input side enters, or on both ports rather, enters at the upper terminal. So the current here is entering the upper terminal of network A, and it is entering the upper terminal of network B. So we have two things that are satisfied where the currents are concerned. One, it satisfies the convention that we had established for two-port networks. And two, it satisfies the criteria for them being in parallel. All right? Now, when you look at the voltage for the two, all right, we look at the voltage for the two. Note, voltage is a difference in potential between 2 points. So here, I have V1. All right, so this is one terminal, and that's another terminal. So that's our port. So the voltage V1 is at that port. And if we just look at the lines here and here, all right, would you agree with me that this voltage is the same as this voltage? Is anybody unclear as to why those two voltages are the same? All right, good. And if we go in the other direction, we'll see that these, again, this port V1, if we go the other direction and go down to B, we'll see that this is also equal to V1. And if we go on port 2, we do the same thing for the current. We have I2, yes? So the current I2, it divides. We have I2B goes to network B, and I2A to network A. And again, V2 would be equal to V2A. So this would also be V2. And V2 is also equal to V2B. All right? Now, students, what we want to also bear in mind is the fact that all of this, yeah? So those two networks forms a single network. All right? And that single network has as at its input V1 and I1 and V2 and I2. So those are the voltages at the input and output of this single network. And again, this single network consists of networks A and network B, or networks A and B. Are we clear? Can we proceed? Everybody have the diagram?
Yes, sir.
All right, thank you. All right. So our objective then is to, as before, find a set of parameters which would link I2 and V2 and V1 and I1. All right? So let's go. Bearing in mind, so the key things we need to take into consideration is that V1 is equal to V1A, and it's also equal to V1B, and V2 is equal to V2B and V2A. I2 would be equal to I2B plus I2A, and I1 would be equal to I1B plus I1A. All right? Okay. So for network A, I can write the admittance or use the admittance parameters of network A for these two equations. So using the admittance parameters for network A. All right. So we have I1A, and remember admittance gives us the current with respect to the voltages, yes? The currents with respect to the voltages. So for network A, this is true, and for network B, that's true. All right. Now, I have these two equations for network A and network B. But as we said just now, I1, yes, was equal to I1A plus I1B. And also I2 would have been equal to I2A plus I2B. So I simply can add these two. And we also know that the voltages were equal. So based on the combined network, all of what we have here is true. We know that the voltages at the input side are all equal. The voltages on the output side are all equal. And then, of course, I1. So on the input side, we have 1A plus 1B. That's I1. And on the output side, we have 2A plus 2B. Okay? So if I make these substitutions, ladies and gentlemen, if I make these substitutions, what I have is that I1 will be equal to Y11A plus Y11B times V1. y12a plus y12b, v2, and so forth. I2, y21a, y21b times v1, y22a and 22b times v2. So all we're doing here is to add the corresponding points within the matrix. Or we're adding two matrices, eh? So in essence, or in summary, the total admittance parameters or the admittance parameters for the combined networks would be YA plus YB. So if we have two networks that are in parallel, if we can show that the networks are in parallel, and again I go back to the point we made, they are in parallel if we can show where the current divides between the two networks and show where the voltages are equal. Then we know that they are connected in parallel. If they are in parallel, then we can find the admittance parameters of each and simply add them. And then we get the combined admittance parameters. Once I have these admittance parameters, I can do anything with them. I can convert them because I know we have been exposed to the conversion matrix. So I can convert these to transmission, to hybrid, to impedance, you name it, depending on what I need to do with the parameters. Any questions? Crystal clear? Okay. All right, so we can now move to the next set of connections. And that would, of course, be if we have the networks in series. So let's take that for me.
Good evening, sir. Dr. Isaac.
Afternoon.
So I have a question, sir.
Go ahead, I'm listening.
Yeah. At the start of the semester, you mentioned something about some labs and was saying that there were some persons who may have done the lab already using the lab course one, and those who had not done so would need to do it. I'm not sure what are the labs and if they are posted and how do we go about getting these labs done.
We're still sorting that out, and we want to ensure that whatever we do, that we are doing it for all the individuals who are legitimately registered for the module. So we'll wait until the census has been completed. And everybody, because I gather the other school also pointed out to me earlier today that not everyone that I am teaching now have completed registration. So we want to ensure that all of that is sorted out before we move forward.
Okay, sir.
So we should ignore that error at the bottom right hand corner.
All right. So here we have two networks connected in series. All right. Well, let's again figure out, why they are connected in series. Now, folks, let's start on the input side. You agree with me that I1 and I1A would be the same, okay? Now, because the current I1A is entering the upper terminal, you would also agree that the current on the return side, all right, the current on the return side, so this current would also be I1A. Now, that current is the same current entering network B. Again, let's go back to our basic definitions. Yes, that two elements are in series if the current leaving one is the same current entering the other. All right, and I hope at this stage in your exposure to networks, when you can begin to appreciate that, that definition of, they are in series because they are connected end to end, no longer, provide any real clarity for you. Yes? Here, current leaving one element is the same current entering the other. So for that reason, because we know that 1A enters here, 1A is leaving here, it is the same current entering network B. So in a sense, what we are saying is that I1 is equal to I1A, and it's equal to I1B. All right? That is telling us that they are in series. The same thing is true on the on port 2. I2 enters network A. I2A would be the current leaving network A. Yes? And it is the same current that leaves network A that is entering network B. And so A and B are in series. Let's also look at the voltages. All right, for the voltages, this is V2. All right, this is V2. V2, which is the potential between these two terminals, would be equal to the potential here plus the potential here. All right, because again, we are dealing with long parameter circuits, it means that these 2 points would be at the same potential. Okay, so equipotential. So V2 would be equal to 2A plus 2B. Similarly, over here, that's V1. It would be equal to the potential here, potential difference there, sorry, plus the potential difference there. All right, so V1 would be equal to 1A plus 1B. All right. Okay. Any questions? Is that clear? All right. So we have our two networks in series, and with our networks in series, Just as we did before with the parallel networks, we can use the parameters for each network, but in this instance, we are going to use the impedance parameters, right? So for network A, using the impedance parameters for A and B, we have V1A, given by that expression, V2A, we have V1B, and V2B. All right, so going back to what we described with the networks, we have I1A being equal to I1B being equal to I1, I2A equal to B equal I2. And of course, for the voltages, V1 would be V1A plus 1B, and V2 would be equal to V2A plus V2B. And we're going to make the substitution as before. So we have 1A plus 1B, and we have 2A plus 2B. So we make the substitution similar to what we did before. And in making that substitution, we end up with this relationship. All right, so for the, just to quickly summarize, for networks connected in parallel, the admittance parameters for the combination would be the sum of the admittance parameters of each network. If you have 3 networks in parallel, yes, then you'll add the 3 parameters, sets of parameters. All right. For networks in series, the sum of the impedance parameters. So we have looked at 2. I don't know what's wrong with me today. We have looked at 2 of the 3 possible connections. Thirdly, one that we have not looked at up to this point in terms of networks one, we refer to it as cascade. And what does cascade represent? So if the networks are now connected in cascade, how will that change our analysis? And by the way, this connection is one that you're going to be using a lot more often than series and parallel in your engineering career. And what we have here is that, technically speaking, we are feeding the output of one network into the input of the other. Now, I must confess that the analysis on this one is not as simple as the other two, but in the end, you will appreciate the summary statement. Okay. So for cascade, couple of things. On the input side, I1 is equal to I1A. V1 is equal to V1A. On the output side, I2 is equal to I2B, and V2 is equal to V2B. It's in the middle that we have a little confusion. Here, I2A would be equal to the negative of I1B, because obviously they are going in opposite directions, yes? And V2A is equal to V1B. So in other words, the output voltage of network A is equal to the input voltage of network B. The output current of network A is the negative of the input current in network B. All right? Now I'll tell you up front that the parameters that we'll be looking at here, yes, and by virtue of what cascade represents, meaning, as we said just now, the output of one network forms the input, right? So it is transferred to the other network. Right? Little weak, but all we're talking about is transmission. So we're transmitting the output of one into the input of the other. All right? Do we have all of this?
Not yet, sir. sir. Finish, sir.
All right, good. Okay, so for network A, and remember for transmission parameters, we are looking at the input with input voltage and current, yes, with respect to the output voltage and current. So for network A, we have V1A equal AA V2A minus BAI2A. Yep. And then for the current, we have C and D. All right. So we have V equal A V BI and I equal CV DI. All right. Now, once I have these defined for the network, I can now look back at the connections and what we said earlier in terms of what was equal to what. We can just note those and then make the substitutions. All right. So when we look at both networks, we look at the connections.
Sir, whenever finish writing us, sir. Okay, sir, finish now.
Okay. So based on the network connections, we had already said this, but just to note them. On the output side, B2 equal V2, I2B equal I2. On the input side, we have I1B equal to I1A, and V1A equal V1. All right, body others. Okay. So we make the substitutions, all right? Remember V1A was equal to V1, so we make that substitution. I1A was equal to I1, we make that substitution. Similarly, on the output side, we make the substitution for V2 and I2. All right, so those are the substitutions we have made. Now, if we just go back to, before I make the other substitutions, I want to go back to the network so that we are all clear as to what is about to happen. All right. So let's go back to the network briefly. We know that 2A is equal to 1B. We also know that 2A is equal to minus 1B. All right? So 2A is equal to 1B. So we're going to make those substitutions. All right? So let's go back now. So these are the substitutions that we are going to focus on. All right? So remember we said that 2A was equal to 1B, and that 2A was equal to, or minus 2A was equal to 1B. All right? Good. So making those substitutions, we end up with this. So making the substitution for 1B, V1B that is, and or 2A depending on it, and then making the substitution there for 1I1B. And then if we expand and simplify, bearing in mind that the relationship we want for transmission coefficient parameters is that V1 is equal to A V2 minus B I2.
Sir, can you go back over that for me, please?
The substitutions?
Yes, sir.
Two A is equal to 1B. We call it that?
Yes, sir. Yes, sir.
All right. And I2A is equal to the negative of I1B.
Yes, sir.
All right. Okay. So having that, we made the initial substitutions at this point so that V1A was equal to V1, so we could make that substitution right off. I1A was equal to I1. On the output side, V2B, remember this is the equation, these are the equations that we had. So this is equal to V1, this is equal to I1. This is equal to V2, this is equal to I2. So those are the initial substitutions we made to get these two sets of equations. We go back to the network, and in looking at the network, we see that 2A was equal to 1B. We also saw that I2A was equal to the negative of I1B. All right? So we are making those substitutions. So V1B, this is V1B. I'm going to substitute it here. This is I1B. I'm going to substitute it here. Let me use a different color. I'm going to substitute it here for I2A or minus I2A. So we make that substitution, and that's what we have.
Okay, sir. Thank you.
No problem. All right, so that's for the voltage side. Okay, so we do the same for the current. Make the substitution for the current, and we get that. All right. So we can now put both equations together. So we have the voltage and current equations, and that will give us the transmission equation for our combined network. And what it may not be very obvious, but from this, we see that the overall transmission for the combined networks would be the product of the transmission parameters. So for both networks connected in Cascade, the overall transmission parameters will be equal to TA times TB. All right. So in summary, if they are in parallel, we add the admittance parameters. If they are in series, we add the impedance parameters. And if they are in cascade, then we multiply the transmission parameters. And this will give us the overall of the combined networks. All right. Any questions so far? Because we're now going to run to some application. All right. No questions, we just proceed then. So take this question from a place. And while you do that, deal with the register. Okay. Just a quick one. Who is Orlando? What's the last person's name? The person's last name? Who is Orlando? Orlando going once, twice. All right. Okay. So here we have a network. And the first thing we need to determine is how are these. Well, first of all, we are told it's two networks, so I suppose that removes part of the mystery. But if we weren't told, then we have to find a way of determining how we can separate the networks, or if there is need to separate it. All right. What we have here, we are told that they are in parallel. So let us look on, which elements really form each of the networks and how is it that they are in parallel, because that's important. All right. Again, by definition, we can see that, let's put in our currents. So we have I1 here. We know that that's V1. That's V2. That's I2. We are told that they are in parallel. So therefore, by virtue of what we have, then we know that we'll have current separating here and here. Okay? So if we did that, then, sorry. Whoops. That was not the plan. Not sure what I did just now. Okay. So these would represent, students, the two networks. All right? So this is my I1, going back to what we just showed. This would be my I1. I haven't changed anything. That's V1. This is V2. And this is I2. Yep. The currents. So let's call that 2A. Let's call that 2B. So it means that this would be 1A and this would be 1B. All right. Okay. Can I move on now?
1 second.
Yes, sir.
1 second, sir.
Whenever you're ready, sir.
Okay. So I want you to go ahead and just using this as a network, right? So just using this as a network. Let's find the admittance parameters for me. Then again, in the interest of time, I'll just do it. I'll just give it to you. So for network A, that will be the admittance parameters. All right. And if we took for network B, that's with the 3 resistors, then that's what we have. And from theory, we're saying that for the combined network, because they are in parallel, yes, we just be adding the admittance parameters of each network. So when we add the parameters for network A to that of B, for the combined network, we get that.
Sir,
Yes.
if we're simply adding the two network Y parameters, sir, why would we negate the entire section down? Oh, never mind,
Okay.
sir. All right.
All right.
I just realized, sir.
Okay. All right. Any other question?
Sir, for Y11, sir, G over a half. Why is that positive, sir?
That's for network A?
Yes, sir.
Mm-hmm.
I'm just asking for Y11, why is it positive instead of it being negative because of the capacitor?
This is the network we're looking at. Huh? These are short circuit parameters, right?
Yes, sir.
If I do this, what's the impedance being looking into that?
Impedance. Yeah. Yes, sir.
What's the impedance? This is minus J2. What's the impedance?
Sir, did I say minus J2, sir?
Pardon?
Minus J2?
Okay, what's the reciprocal?
1 second, sir.
1 over that. All right?
Okay, sir.
All right. So we have we're told that they were connected in parallel, but I could rearrange the elements to let them look like they are in series. I've done nothing to the network. I've changed nothing. All right. So if I go back to the original network, all right, that's the original circuit. If I make this, instead of connecting this here, nice and neat, I make this like that, right, and connect it down here. Would I have changed anything? No. All right, which is what we have done here. We haven't changed anything. It's the same potential at the base of the 1 and the 2 ohm resistor. So I've just pulled down the base of the 1 and the 2 ohm. They are now vertical. So is there anyone who disagrees that this circuit is the same as the circuit as the original? All right, so with this circuit, what we therefore have are, let's call this network A. Let's call this network B. All right, so this is A and this is B. So what we now have are two networks in series. Do you agree with that? Is anyone who is unsure or unclear why they are in series?
Sir, could you go over it one more time?
Huh?
Let's go over it one more time, sir.
What I asked for that? Was that Miss Ellis?
Montague, sir.
All right, so let's work it through, Miss Montague. Let's work it through. This is I1. Okay, let's get some markings on this. So that's I1. Agreed?
Yes, sir.
Remember now, this is the network we're looking at. This network, all right? So would you agree that I1 would be the current? Would you agree that I1 would be the current coming out at that point?
Yes, sir.
And where is that current heading?
It's heading into network B.
All right, so the current leaving A is the current entering B. All right, and if the current leaving network A is the same current entering network B, what can we say about the two networks?
They're in series, sir.
You agree with that, Ms. Montague? She has disappeared. All right, so both networks are in series. So up here, we'd have 2B, and here we'd have 2A rather, and here we'd have 2B, and we'd have 1B, 1A. All right, so take those two networks for me. I give you a couple minutes to make an attempt. So take these two networks, find for me the impedance parameters of the network at the top and the impedance parameters for this network. And then we are going to add them and see where we go from there. All right? So I give you, it's now 6:30, I give you 10 minutes with this. All right. So I gave you a little more time than I intended. So for the network at the top, anybody get the matrix? What would be the impedance matrix?
Not sure. Not sure if it's right. I got 10 over 13 minus 2 over 13 J.
10 over?
10 over 13 minus 2 over 13 J.
Okay.
And next, what I got the same thing for the next one next to it, sir. That's I wasn't sure about it.
You got 2. The next one you got this 10 over 13 minus J2 over 13.
Yes, sir, and I got the same thing corresponding for the next matrix. Only one that changed, sir, from is was the 14 over 13 minus 8 over 13J, which would be for V2.
Another one you got what?
For Y, no, sorry, Z22, sir, I got 14 over 13 minus 8 over 13J.
14 over 13 minus J8 over 13.
Yes, sir. One corresponding next to it, so I got the same 10 over 13 minus 2 over 13. Sir.
Is that for the combined network or just for
No, you wanted the combined one, sir? No,
I'm asking. Is that for the combined?
ZA, sir.
Oh, ZA. Did anybody get anything different? All right, let's look at the network quickly. Mr. Lewis, you're the one who gave me those values? Was that
Watson,
Lewis?
Nikolai, sir.
Oh, Watson, okay. All right. And this was minus J2. Okay. So, so Watson, tell me how you went about finding Z11. So this is I1, this is V1, that's I2, and that's V2. So how did you go about finding Z11?
Sir, I found the total impedance, sir.
What did you do with port 2?
Left it open, sir.
Okay. So for the input, it would be. Go ahead.
For input, sorry, for the input, sir, would be the 1 ohm.
Go ahead, man. In parallel.
In parallel to the minus 2J, which is the imaginary, plus the 2 ohm.
All right, so that is 2 minus J2.
Yes, sir.
All right. And that's product over sum. So what would that be equal to?
That the 10 over 13 minus.
No, just keep it simple. If I multiply 1 by this, what do I get?
Oh, 2 minus J2, sir.
Over?
3 minus J2.
All right. So leave it like that for the time being.
All right, yes, sir.
All right. So that is Z11. And of course, over J2. And that would, of course, be 2 over 13. Agreed?
Yes, sir.
Or if we multiply these two, if we rationalize.
Sir, I now see 2 over 13, sir.
If we rationalize, we have 2 minus J2 times 3 plus J2 over 13. That's what you went about, Mr. Watson?
It just came up in the, I got it in the fraction in the calculator, sir. As it. When I plug it in the calculator.
Okay. So if we do this, yes, we'd have 6 plus 4. And this would be where am I? 2, 3, 6, 2, 2, so that would be J4. And then minus J6. Agree? Over 13. So this would give me 10 minus J2. All right?
Yes, sir.
So we can agree that these two are the same, all right?
Yes, sir.
So that one seems fine.
All right. So the next one now, sir, to be V1.
All right. So let us deal with the transfer. Let's deal with the transfer. Let me all right, let me just see. For the transfer, what we're looking for with the same open circuit, yeah? Because port 2 is open. We're looking for Z21. So Z21, right? That
Yes,
would be V2 over I1.
I1, yes, sir.
All right, so let's look at I1. Where is I1 flowing? I1 is entering our network, yes?
Enters the nodes and splits them.
Right? So what is the current that would go towards the 2 ohm, which is where V2 is? What is that current in terms of I1 that would be flowing through the 2 ohm?
Sir, that would be the current across will be 1 minus 2.
No, we don't use them terms, Mr. Watson.
Repeat that then, sir.
No, you said it's a current across. Come, we don't do that. We're in the second level.
My mistake, sir.
So go again.
So I got 1 minus 2J I2.
Why is it 1 minus? What are you multiplying? What are you doing? Why are you subtracting?
I'm finding the current, sir. So I'm finding the current across the.
You come back with the current across. It's current through, Mr. Watson. Come on.
So, I'm finding the current through the J2 and the 2 ohm resistor, sir.
Yes. So what method are you gonna apply?
Current divider.
Okay, and if you're dividing I1 between those two, how would you do that?
Oh, I see the mistake I made now, sir.
So you use current divider, so it would be I1 times 1.
Yes, sir.
Agreed?
Yes, sir.
Over 3
Over
minus
3
J2.
minus 2J. Yes, sir.
Yes. And so when you multiply to get V2, it will be 2I1, and that's equal to V2. Agreed?
Yes, sir.
So it means that Z21 would be equal to 2 over 3 minus J2.
Agree, sir.
Good. And I appreciate the effort, Mr. Watson. That's excellent. I applaud it. At least you're making an attempt, and I appreciate that. All right?
So I did try something to say, but I never rationalize.
But you don't need to rationalize, you know.
So when we did hear Mr. Watson talk, so I just feel like me totally wrong.
Pardon me?
So when me hear Mr. Watson talk and you write it down, I just feel like me totally wrong. So I just nobody else know.
You have here, and this, when you work it out, you'll find that this is also equal to Z12. Okay? And then for the impedance, you're looking in this direction. So it is 2 in parallel with 1 minus J2. So this will be 2 minus J4 over 3 minus J2. Okay? So this is Z22. So you now have Z22, you have Z12, you have Z21, and you have Z11. All right, now for the single resistor, what are the impedance parameters? Nobody got that far?
No, sir.
One right throughout, sir.
One right throughout, yeah.
Huh?
Yeah,
one, sir.
One minus 1, and then minus 1, 1.
One, 1, 1, 1. All right?
Yes, sir.
You add the two, and you'll get the overall Z. And what I needed to do is then to find Z inverse, and this should be equal to the Y that you had calculated earlier. Fair enough?
Yes, sir.
All right. So we're just about wrapping. So take this question for me. All right. So, with the exception of the tutorial that we have scheduled for Wednesday, where we look at these connections and just look back at some of the questions that we have already done and see how using this, what we had done this afternoon into evening, could assist in our analysis. Once we have gone through that, then you would have completed all the material for test number 1, which I remind you is scheduled for July 3. Yes. Yeah. So once we have done that, then that would be the end of two-port networks. All right. So we look at this question and a couple others on Wednesday, God's willing. So that said, have a good evening.
Sir.
Yes, sir.
What time is it on the 3rd of July?
Pardon me?
What time would be the test on the 3rd of July?
It's in your module outline. All that information is in your module outline. All right, good. Take care.